So we've talked a lot about groundwater, what it is, where it is, how it gets there, and its interaction with surface waters. Groundwater is really important as a resource. We use it, we create issues with using it. There's also limits to using it. So let's go over some of those details. Why do we bother using groundwater? Why do we bother drilling down and pumping out water from inside the earth instead of just using plain old surface water like from a stream or from a pond? It basically comes down to these 5 things. It's cleaner, so surface water is much easier polluted, and groundwater, as it's flowing through the aquifer and through soil, gets kind of filtered out. So groundwater comes out already cleaner. There's also the idea of population density. So in the town of Boone, the population density is pretty high. All those nooks and crannies and neighborhoods in the town, they are supplied water by the town, and you pay for the water. On the outskirts of Boone, in the county, out in Watauga County, Sugar Grove, Todd, Vilas, Valley Cruces, Fosco, New Camp. I live in Boone, but I live north of town over Howard's Knob. There's just not enough population density to merit having the infrastructure that would put town water out to these houses. So it just is easier and makes more sense to drill down and get groundwater. Next, stream flow varies over time. We've seen this by looking at hydrographs. We've looked at them in lab, and we've looked at them some in lecture. The stream flow is going to fluctuate. When there's no rain, the stream level can drop. When there's more rain, we have floods, and flooding often introduces contaminants. But the groundwater supply is pretty consistent. Sometimes a shallow well can dry up if it's seasonally dry, but for the most part, groundwater flow is consistent. It is indeed true that we can build dams. So for the town of Boone, there are 2 reservoirs. There are also 2 reservoirs for campus. There are reservoirs of water that we drink for drinking water from in town, either campus water or town water, and that works perfectly. They both back each other up if they need to. But if you have a surface water in a reservoir, they're in a more arid environment than Boone, there can be lots of evaporation, and that's bad. One thing they do is they'll put millions of almost like ping pong balls on top of water and let those ping pong balls float on top of the water, and that traps the water and it doesn't allow it to evaporate. So you may see that in images. Okay, and then just there's a limited supply. Groundwater is everywhere, but surface water has to have kind of a unique location. There are consequences, though, of using the groundwater. The first one is if your discharge exceeds your recharge, it can lower the water table and cause something called a Kona depression. We'll see an image of that in a minute. We call that over pumping mining, and that mining can lower lake levels, decrease the discharge in the stream. It can ruin the ecology and the hydrology of wetlands to the point where they can completely dry up, and in that you have habitat loss. When you lose that resource, you're losing the habitat, then there can be pollution in the air and the water associated with that drawdown. Nestle is one of the companies of the world that gets a lot of crap for mining water. Mostly they do it for bottled water. My children know of all the things that makes their mom the maddest, it's drinking bottled water. Don't do it. Don't buy water. Okay. Next up is compaction and surface subsidence. We'll see an image of that, but what it means is when the water is sucked out of the aquifer, the spaces between the grains or the fractures can close, and we saw that can, an extreme level, cause a sinkhole when you pull water out of a cavern beneath the surface, but that happens with all the tiny little voids as well. When that happens, the porosity is decreased and the permeability is decreased, and you can't get that back. There are places in the world where that's happened. Venice, Italy. If you've ever been to Venice, you ride around in a boat to get from here to there, or you go on a crowded sidewalk. Galveston or Houston area of Texas, LA and Southern California. These are all places that are experiencing subsidence, or the actual elevation of the land is sinking because of groundwater loss. Lastly, saltwater intrusion. This is a consequence of using groundwater near the coastlines. When you pull water up through pump it up through a well at the beach near the coastal plain, you're going to suck up the fresh water and eventually get to the point where you're sucking up salt water, and that's called saltwater intrusion. That can ruin the water supply, changes the hydrology of an area. So this happened in Brooklyn in the 30s and basically ended up being a loss of the fresh water supply around New York City. The water in New York City is some of the best in the country. Now, they get their water from the Adirondack snowmelt every year. Alright, so in the natural system, you have recharge through precipitation. The groundwater system is full of water, and then there's some kind of discharge, usually by adding that water to surface water or through springs as well, or into a lake, a natural system. In an altered system, we're going to be pumping out some of that water. And so then on the other end, the discharge is decreased. Here is a look at a cone of depression. We have 4 houses with a water table. They're all using the water. They're using the water a little bit more. The people in the green and the orange houses went to town on watering their lawns. They did a ton of laundry. They flushed the toilet a million times a day. They washed their cars. And maybe they left the toilet running. As a consequence, the water table now is beneath the end of their wells, and now they have to drill deeper to get more water. That can be very expensive. That's a cone of depression. And on the slide here, it looks like a straight line, right, or a curvy dotted line. Imagine, though, it's going to be shaped like a cone. Everybody's putting in a new well. All right, so here's that cone, lowering the water table. So with a little bit of pumping, maybe you have a slight decrease in the elevation of the water table. Then with increased pumping, then you change kind of the whole hydrology of the area. The link here is about the Mississippi embayment and some of the water loss from overpumping and the cone of depression that is around the Mississippi embayment. Okay, so the definition of a cone of depression, it's a decline in the water table that is shaped like an inverted cone. So instead of being like a little volcano, it's like a ice cream cone. Drawdown is the verb, lowering the water table below the pre-pumping conditions. So moving the water table away from the pre-urbanized conditions. In this image, there's a small cone of depression underneath the house. There's a much larger cone of depression underneath the agricultural well there that's irrigating those little lettuces. The cone of depression, is bad in itself because it costs money to keep drilling deeper and deeper. But check out this image. In A, here's the normal conditions. We have a confining unit on the base and an unconfined aquifer open to the water table to the land surface in A. This whole area is the recharge area, and the regional groundwater flow is to the right down to the stream. So we're recharging that stream with the groundwater. The stream is a gaining stream. In B, now, there is a well, and that well has created a cone of depression. The cone of depression then changes the hydrology. So now the water, we're going to say to the east of the well, is starting to flow down that slope of that water table and towards the bottom of the well. More time passes, and now water that was flowing into the stream is now not even flowing into the stream anymore. The stream has become a losing stream. So that's going to decrease the discharge in that stream. These kind of things are bad. They're hard to reverse once they happen, and it's usually, I'm not going to trash Nestle again, but we'll just use it as an example. It's usually something like Nestle's fault, where they have overpumped an area with, quote, spring water, and then the damage is done to the discharge of the stream. Here it is again. In this image, we have factories that are industrial pumping, pulling out that water, and then the water table is dropping, and the stream then is left kind of high and dry. Here is a look at the extraction of water, oil, and gas from around Houston. So Houston, I said Houston and Galveston. Houston's here inland. It's in the coastal plain. Out here at the Gulf of Mexico, like at the beach, is Galveston Island. But the subsidence of the land extends out to Galveston. So these numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 represent how much the land surface has dropped in feet. 10 feet the land surface has dropped, subsided around the Houston area. Land subsidence. Here's the definition of it: the decrease in land elevation due to lowering of pore water pressure, and that is due to groundwater mining, the overuse of groundwater resources that is not being replenished, so it's not getting recharged. The image on the left shows kind of normal conditions. There's a little house out on the prairie. Water is keeping these grains apart in the aquifer, this gray unit. To the right, this is time 2. Now there's intense pivot irrigation in this field, and because of the pivot irrigation, they pull water out of this aquifer, and now some of the pore spaces have collapsed. They're no longer buoyantly being opened by the water. This map shows the United States, and in light blue are the unlithified, unconsolidated aquifer systems of the United States. This area here, that link from above, is the Mississippi embayment, and that is what is subsiding in that link. You can read about that. This area here is the Ogallala Aquifer. I'm going to draw a circle around Ogallala. And then the coastal plain of South and North Carolina into Virginia, Massachusetts, Delaware, that area also has an unconsolidated aquifer. So overpumping those areas can lead to land subsidence. That has happened in California in the San Joaquin Valley. This post here just goes to 77, but showing land subsidence from 1925 to 1955 to 1977. That guy will say is 6 feet tall, 6, 12, 18, 40 feet of subsidence. And that was in 1977 from overpumping. It can cause, so here's in southern Arizona, cause heaving of the landscape, and so they have signs, subsidence area, and there may be an area where the ground is cracking wide open like this. Alright, saltwater intrusion. Here in this diagram on the left is the blue saltwater. Then on the right is the coastal aquifer, that's the freshwater. And the freshwater is floating on top of the saltwater right here at the interface. If the water is overpumped, then the salt water is going to intrude into that system, into the freshwater aquifer, and you'll start sucking up saltwater. Not as bad. You can't drink it. So over here's a normal interface. That is that boundary between the salt and the fresh water. And then so it was here. And now it's sucked up that salt water into this contaminated well. And so, one of the ways they have attempted to fix it is to pump fresh water down into some of the wells that have been damaged. So, trying to recharge the wells to get move that salt water back out to sea. Miami-Dade, they're having these issues with saltwater coming in. These colored lines on the map are showing the saltwater intrusion lines for a given year. So the reds and yellows are older, and the more recent would be the greens, and movement of saltwater inland. And then they are pumping water down in there pumping fresh water in there to push that salt water back out to sea. Alright. Normally, I would have you grab a piece of paper and to make some sketches, you and your neighbor together, but make sure you can do this. Make sure that you can draw the Earth's surface, put a water table in it, maybe over pump that aquifer, create a cone of depression, and be able to label on that map the saturated zone that's beneath the water table, the unsaturated zone that's above the water table, a well going down into it creating the cone depression, and the Earth's surface, and some pretty little trees.